Hello everybody. I wanted to try to teach fundamentals chapter 41 because this will help me study, but at the same time I read the chapter yesterday and I did take breaks, but it took about 8 hours to read through all of chapter 41, and I said all of chapter 41. Most of chapter 41 I'm still reading through some parts because it is an extensive chapter, but I just wanted to try to explain it simply, hopefully. I'll begin with our water distribution, and some of the things that I will explain are also on our PEEP study guide. So beginning with water distribution, our water in our body is in two different compartments, and the two different compartments are the intracellular fluid and the extracellular fluid. Most of the water in our body is in the intracellular fluid space, which is inside the cells. That's 70%. The other 30% is in the ECF. The ECF is further compartmentalized into three spaces. So the subcompartments of the ECF are the intravascular fluid, that's going to be our plasma, the interstitial fluid, that's going to be our lymph, and then the transcellular fluid, that's the third space. If you hear that a patient is third spacing, that's what they're talking about. They're talking about the fluid is in these spaces, which are the intracranial fluid, intraocular fluid of the eyes, the pericardial fluid, that's the fluid that lubricates the two pericardial membranes, the parietal and visceral pericardium of the heart, and the fluid that's in our joints, synovial fluid, and then also the fluid that's between the two layers of the parietal pleurae, so the visceral and the, I'm sorry, not to say parietal, the, bear with me, it's not parietal, let me pause it, I'm having a brain infarct. Okay, I meant to say peritoneum, the parietal and the visceral peritoneum. So those spaces are the places where the transcellular fluid is, and that's when you hear the patient is third spacing, I think they mean edema because there's a large amount of fluid that's not necessarily going into the interstitial fluid, not the lymph necessarily, but I could be wrong, but it's going into the tissues, and maybe they do mean the interstitial fluid, but that's not relevant for this test. We just need to know where our water is distributed. And there may not even be a question about that, but it's good to know. Next, if we move on in the chapter, we know that from what we've heard in lecture that men have more body water than women do. I think men are, the average adult is 60%, isn't it, of fluid? 60% water, total body water. After age 60, it becomes 45%. Men are 60%, women are 50%. After age 60, adults are 45%. Babies are mostly made of water. Sorry to simplify that so much. But we know that there's more water inside muscles than there is in fat. And women, because of anatomical reasons for producing babies, have more fat distribution than men do. Let's see, so how much fluid are we supposed to intake daily? Our fluid intake is 2,600 milliliters daily. That answers one of the PEEP's questions. And it can be measured in sensible losses. We cannot measure insensible losses. So sensible losses are what we can measure: urination, defecation, and wounds. I just saw it when it wounds. I just saw the Jackson Pratt drainage. Just thinking of that bulb and how we can measure within the bulb, we can measure the wound drainage. Or even when we have a wound dressing, we can estimate the drainage by the percentage on the wound dressing. Insensible water losses are water losses that we cannot measure. It's impossible to measure. For example, evaporation from the skin, vapors from our lungs during respirations. Evaporation from the skin would be sweating. We really can't measure our sweat. We can just kind of approximate how much we sweat every day. My notes are starting to go into cations and anions. So that's getting into electrolytes. We know that cations have the positive charge, anions have a negative charge. So these were molecules that dissociated in the water. That's what the definition of what an electrolyte is a molecule that dissolved in water and bears an electrical charge. So for example, in order to help this make sense, a grain of salt is maybe not as simple as this, but just to make sense of it, a grain of salt is sodium chloride, so NaCl. When it dissolves in water, it becomes sodium Na+, and chloride Cl-, because sodium has the positive charge, chloride has the negative charge, and when they combine, they become electroneutral. So if we're talking about our body, the major cations of our body are sodium, Na+, potassium, K+, magnesium, Mg2+, calcium, Ca2+, and then a proton, which is hydrogen ion, H+. The major anions of our body are chloride, Cl-, bicarbonate ion, HCO3-, and then phosphate. Phosphorus is our electrolyte, but I just don't really know how to explain it, but phosphorus in our body is in the form of phosphate. PO₄ it's either minus or 2-. Non-electrolytes, because not all of the important molecules of our body that contribute to acid-base balance, and we're still talking about fluid, volume, and electrolytes before we get into acid-base balance, but I just wanted to clarify that there are some non-electrolytes that are important. They don't have a charge, but they're important for the acid-base balance, and that's going to be urea and glucose. I won't do that so much, and I know my voice sounds like sandpaper, and I'm tired. But getting into the ECF electrolytes, so our major electrolytes that are outside of the cell are sodium, that's our major cation, chloride, calcium, and bicarbonate. Our major ICF electrolytes within the cell, potassium, that's our major cation in the cell. So our major cation out of the cell is sodium, in the cell is potassium. Also within the cell, our major anion is phosphate. And then our major, it's not major, but also within the cell is sodium's, I want to call it sodium's counterpart, but I'll hold off on that for now because I don't want to cause confusion, but magnesium. Magnesium, sodium, phosphate are inside the cell. Outside of the cell, sodium, chloride, like salt, calcium, and bicarbonate ion. So talking about these electrolytes, before we get into acid-base balance, I think what I'm going to talk about now is it talking about, give me one moment. Okay, so I'm talking about the reason the electrolytes are important in our body. So sodium, our normal range for sodium is 135 to 145. We're not going to, the book does say 136 to 145, but we were told that the test questions on ATI, my battery is low, the test questions on ATI are not going to give a lab value that's on the cusp. It's going to be obviously hypo or hyper in a lab value. So I think it's safe to say 135 to 145 for sodium instead of 136 to 145 is awkward to memorize. So 135 to 145 sodium, it's the major ECF cation. So just telling you more about sodium and what it does in the body is its purpose or function is to balance serum osmolarity. What is osmolarity? Osmolarity is the amount of solute in the serum. It's the amount of particles in the serum. So sodium manages it all. And I want to say the reason it does it is because it can like albumin, where it's not pulling water around, but wherever sodium goes, water follows. And wherever sodium goes, chloride also follows, because chloride's trying to balance sodium's positive electrical charge. They're electroneutral. So what is sodium important for? Muscle contraction. It's a part of the whole I want to say cross bridge activation, but it's a part of muscle contraction and nerve impulses. As you know, the sodium influx into the cell increases. Back in physiology days, the sodium influx into the cell increases the voltage of the cell, making it more positive, closer to its threshold. And then when it reaches threshold, it fires an action potential. So sodium is important for muscle contraction, nerve impulses, and acid-base balance as sodium bicarbonate circulating through the bloodstream. The next major cation is in the ICF, which is potassium. Potassium levels are 3.5 to 5.0 milliequivalents per liter. Another lab value that is 3.5 to 5.0 is albumin, just to remember those two lab values are similar. 3.5 to 5 potassium controls the same as what sodium does on the outside of the cell, potassium does on the inside. It controls the ICF osmolarity, so just to think about it simply, the particles within the cell, but it also regulates cellular enzyme activities, and our enzymes are what lower the activation energy so that our cells can perform so that our cells can function. So I'm gathering my thoughts. Okay, so not to go on too many trails because I like to think, but we only have a week and we need to stay focused. What potassium does in the body is it transmits electrical impulses similar to sodium. Muscle contraction is very important. Regulates acid-base balance, sounds a lot like sodium. But something very interesting about potassium is that when hydrogen, the protons, are increased when we're acidotic, then the cells will start exchanging. This is one of the mechanisms of homeostasis. The cells will start exchanging potassium for hydrogen, but I'm flipping it around. So the cells will start, so here is potassium inside the cell, here's hydrogen outside of the cell, and they will exchange for each other. So hydrogen goes into the cell, potassium comes out of the cell, and now potassium's in the bloodstream. And this, I need to verify this, but it may cause hyperkalemia, but I need to verify that. So where do we find, for sodium, how do we, just going back to sodium, I know I'm talking about potassium, but I forgot to say this. For sodium, we get our sodium from foods, such as processed foods with sodium. For potassium, we also get our potassium through intake. So it's from fruits, vegetables, legumes, whole grains, milk, meat, and according to ATI, we also, the fruits that they were particular about in the questions were canned apricots and, okay, brain infarct, avocados. And I'll take a break. Next is calcium. We have two types of calcium in our bloodstream. We have free ionized calcium, and we have calcium that's binded to proteins. The calcium that we're interested in, the calcium that we're interested in is the calcium binded to proteins. And the book gives us about 8.6 to 10.2 milligrams per deciliter. This and phosphate are the two electrolytes that do not have a milliequivalent per liter unit. This is the one that has milligrams per deciliter. It's maybe just memorize 8.6 to 10.2. I want to just say 9 to 10 for it, but what if the lab value is 8.6 or on the test? So just memorize 8.6 to 10.2. But kind of maybe your parameters is to know that it's approximate to 9 and 10 for calcium. And its role is blood coagulation. So we need calcium for forming blood clots so we don't hemorrhage to death. And it's also important for the transmission of nerve impulses, regular muscle contraction, just like sodium and potassium. And it's a regular component of bones and teeth. That's where it's stored. Our next electrolyte is magnesium. Our magnesium levels are 1.3 to 2.3 milliequivalents per liter. I didn't write it down for calcium, but we do absorb calcium through our dietary intake. And it's also important that we are I'm trying to say efficient, that we eat enough vitamin D, that not just eating it, but that we're absorbing it, that we don't absorb vitamin D from the sunlight, but when we go into the sunlight, the UV rays activate vitamin D synthesis in our body, and we're able to synthesize vitamin D through the UV rays, through our dietary intake of other nutrients. And vitamin D is important for absorbing calcium because especially in women, and men too, I don't know why I'm saying just women, vitamin D is a part of the villi system in the intestines. So vitamin D kind of is the key that opens the villi to absorb calcium from our diet. Estrogen plays a role there too. And the reason it's, I was saying important to women is because women as we age, after menopause, we don't make as much estrogen, and estrogen deficiency inhibits us from absorbing calcium from our diet. So women are prone to bone breakdown, bone fractures, osteoporosis. So getting back on track, that's one of the purposes of calcium is our bone and teeth. That's where it's stored in it, and it also is a major component in the I want to say integrity, in the strength of our bones. The next that I mentioned is magnesium. It helps us to metabolize carbs, proteins. It's also important for neuromuscular function. It acts on the cardiovascular system by producing vasodilation. So it's important for vasodilation. I've often heard magnesium is one of the electrolytes that we have deficiencies in, that most people have a deficiency in magnesium. Maybe it's because it comes from leafy greens, and I don't know. I'm not trying to solve that. Don't want to say that, but okay, I feel like I was getting off track there. I want to solve the problems, but for the purpose of this chapter, magnesium comes from leafy greens, nuts, seafood, whole grains, beans, cocoa. I've heard of, not to go on another trail, but I've heard of copper coming from 100% cacao chocolate. But here is magnesium with cocoa, and it's lost via urine and loop diuretics. And I want to say most of our electrolytes are depleted with loop diuretics. Chloride is the next. Let's see, we have chloride, bicarbonate ion, and phosphate. And then I'll talk about tonicity, and then I'll start a new recording for acid-base balance. Let me just plan here, I'll pause it. Chloride is the mnemonic that we've heard about the swimming pool. 97 degrees to 107 degrees is when it's ideal to go swimming. 97 to 107 milliequivalents per liter. Chloride is the major component of interstitial fluid. It's the major component of the lymph. It's also in the stomach. It is already in the stomach, and the parietal cells are producing the protons and the chloride, pumping them into the stomach, the gastric lumen, and then that's where they combine and form hydrochloric acid. So it's also in pancreatic juices, sweat, bile that's stored in the gallbladder, and saliva. It acts with sodium because they're electroneutral. It acts with sodium to maintain osmotic pressure, and this is what I'm talking about, the pooling of water. And I'll talk about pressures before ending this recording. It combines with hydrogen to produce, as I mentioned, hydrochloric acid. The next electrolyte is bicarbonate ion, which is regulating our acid-base balance. Hydrogen and bicarbonate ion are our two electrolytes of acid-base balance in regards to our chemical buffers. Our level of bicarbonate is 25 to 29. We should think of some way to remember that. It makes me think of ages for some reason. Ages 25 to 29. Bicarbonate. Doesn't make sense. Okay. It's lost by diarrhea. So when a patient is having an excessive amount of diarrhea, when they're having diarrhea, they're losing their base, bicarbonate, and what happens is metabolic acidosis can occur. The next electrolyte is phosphate. It's the major intracellular anion, as I mentioned. Its range is 2.5 to 4.5 milligrams per deciliter, according to the book. There's an MEQ measurement. I still need to find that one because I just have the measurements from the book. It's a hydrogen buffer within the cell. It promotes energy storage in the mitochondria. It's important for bone and teeth formation because it's I want to say it has an inverse relationship with calcium, but I could be wrong about it being inverse. But it does have a relationship with calcium in the bones. Our bones store calcium and phosphorus. And it's very important for muscle and red blood cell function. Okay, so when we're talking about blood, our major electrolytes are the electrolyte that causes coagulation, which is calcium. Our electrolyte that causes vasodilation, which is magnesium. Let me check that to verify that. Yes, vasodilation, magnesium. And our electrolyte that's important for red blood cell formation or function, red blood cell function, is phosphate. So just chunking that information together there, since we have so much information, I think it's important to chunk some information. So total cations are normally equal to anions in the body. So just may help you understand homeostasis if you know that the amount of positive charges are equal to the amount of negative charges in the body to maintain homeostasis, to maintain electroneutrality. Let's see. So this is talking about the body producing balance by shifting fluids and solutes between the ECF and ICF. So what is responsible for this? Organs, body systems, capillary filtration, osmosis, diffusion, and active transport. So these are the processes that the body goes through in order to maintain fluid balance and electrolyte balance. Because right now we're just talking about fluids and electrolytes. We're going to talk about acid-base balance in the next recording. So osmosis is, we're going to be talking about our serum. So we learned about isotonic solutions, hypotonic solutions, and hypertonic solutions. So instead of a solution, we're talking about our serum, because we're talking about our blood. So isotonic solutions are when our blood is isotonic, is when there's a neutral amount of solutes in the ICF and in the ECF. Okay. Hypotonic is when there is less solutes in the ECF than within the cell. Hypertonic is when there's more solutes within the blood than there is in the cell. And so hypotonic, when I mentioned that there's more solutes in the cell, cells swell, because the fluid in the extracellular fluid will, or extracellular space, will enter the cell in order to achieve neutrality. Hypertonic is when there's more solute within the serum than there is in the cell. So then cells shrink, because the fluid in the cell is going to try to reach equilibrium with the particles that are, or the solutes that are inside the serum. How is this achieved? By capillary filtration is one way. Our capillary filtration is our hydrostatic pressure, which is the pushing force of the fluid against the cell walls, or we'll just say the endothelium of the capillaries. So that's the capillary walls. The fluid pushing against the capillary walls is our hydrostatic pressure, and our oncotic colloidal pressure is the pulling force. Capillaries should have 0 for their oncotic pressure. Not the capillaries, but the capillary space. And that's what I'm talking about, the kidneys. But proteins, our major plasma proteins, are albumin. That's the big one. Albumin should be inside the bloodstream. It should not be outside of the bloodstream, because if it is, that indicates a problem, like at the kidneys. If it's and I'm sorry I'm saying like, I'm just trying to explain this. If there's a problem at the kidneys with the glomerulus, then there might be some inflammation that's causing the fenestrations of the capillaries. There's some little openings that allow nutrients and electrolytes to enter in, to be absorbed, to be excreted. It's allowing entry and exit of those smaller particles, but larger trying to explain this. Larger particles such as albumin are not allowed to leave the bloodstream because it's larger than the openings, and so it stays inside, basically like a colander, and it can't pass through it. So I know that's at the level of the kidneys, but it helps me explain that the proteins in the blood, they're not going to enter the cell either. They're going to stay in the bloodstream, and they help such proteins such as albumin. They help pull water, because albumin's the water magnet. They help pull fluid into the intravascular space. So when a patient is third spacing, they may be, I know that our instructor said crystalloids, but I did see a patient that was prescribed albumin because she had edema. So they may be prescribed a colloidal IV, such as albumin, which is, colloid means protein. Oncotic also means protein. So when you hear oncotic pressure, colloidal pressure, or colloidal substance, they're talking about a protein. And it pulls, it has a pulling force, not a pushing force, not pushing water. It's attracting the water to it. So it has a pulling force. Okay, I'm going to stop there and then record about acid-base balance. I hope this helps.